What specific problem does the Byte Latent Transformer, BLT, aim to solve in the context of existing large language models, and what shortcomings in tokenization does it address?
The Byte Latent Transformer, BLT, aims to solve the inefficiencies and biases introduced by tokenization in existing large language models, LLMs. Tokenization, as a heuristic pre-processing step, groups bytes into a static set of tokens, which can lead to domain sensitivity, input noise sensitivity, and a lack of orthographic knowledge. BLT addresses these shortcomings by directly learning from raw byte data without a fixed vocabulary, allowing for dynamic allocation of compute based on the complexity of predictions. This results in improved robustness to noisy inputs and enhanced character-level understanding, which tokenization-based models often miss. Additionally, BLT's architecture enables more efficient compute allocation, achieving performance parity with models like Llama 3 while using up to 50% fewer flops at inference.
How does the proposed BLT method work? Illustrate its architecture step by step, particularly focusing on the patching mechanism and the allocation of compute resources.
The Byte Latent Transformer, BLT, operates by dynamically allocating compute resources based on the complexity of byte sequences, utilizing a unique patching mechanism. Its architecture consists of three main components: two smaller local models, encoder and decoder, that handle byte sequences, and a larger global latent transformer that processes patch representations. The patching mechanism is central to BLT, where bytes are grouped into patches based on the entropy of next byte predictions, allowing for contextualized and efficient processing. This dynamic patching enables the model to allocate more compute to complex predictions, such as the beginning of sentences, while using lighter computations for simpler tasks, like predicting common word endings. Overall, BLT achieves improved efficiency by adapting the compute allocation to the information density of the input, resulting in significant reductions in flops during inference compared to traditional tokenization-based models.
Can you provide a simple yet illustrative example to demonstrate how the BLT algorithm segments bytes into patches and processes them during inference?
The BLT algorithm segments bytes into patches using a method called entropy patching, which identifies high uncertainty next byte predictions to determine patch boundaries. For instance, if the algorithm processes the byte sequence "the quick brown fox," it might calculate the entropy of predicting the next byte after each byte in the sequence. When it encounters a byte with high entropy, indicating a more complex prediction, it creates a patch boundary there. During inference, the BLT model then processes these patches, dynamically allocating more compute resources to the patches with higher entropy, such as the beginning of the sentence, while using less compute for simpler predictions, like the ending of common words. This approach allows BLT to efficiently manage computational resources while maintaining performance, as it can adaptively group bytes based on their contextual complexity.
What theoretical or practical benefits does BLT provide when compared to traditional tokenization-based models, especially in terms of efficiency and robustness against noisy inputs?
The Byte Latent Transformer, BLT, offers significant theoretical and practical advantages over traditional tokenization-based models, particularly in efficiency and robustness. Firstly, BLT dynamically allocates compute resources based on the complexity of predictions, allowing for more efficient processing by using a learnable method for grouping bytes into patches, which can save up to 50% in flops during inference compared to fixed token models. This contrasts with tokenization-based models that allocate the same compute to every token, often leading to inefficiencies. Secondly, BLT demonstrates enhanced robustness to noisy inputs as it directly models raw byte data, which allows it to better handle variations and noise in the input, outperforming tokenizer-based models in robustness evaluations by an average of 8 points. Additionally, BLT's architecture enables improved character-level understanding, which is crucial for tasks involving orthographic knowledge and low-resource machine translation, areas where traditional models struggle. Overall, BLT's approach not only enhances computational efficiency but also significantly improves performance in challenging input scenarios.
How is the effectiveness of BLT validated in the paper? Describe the experimental setup, including datasets and evaluation metrics used to benchmark it against tokenization-based models.
The effectiveness of the Byte Latent Transformer, BLT, is validated through a series of controlled experiments comparing it against tokenization-based models, specifically Llama 3. The experimental setup involves pre-training BLT on two datasets: the Llama 2 dataset, which consists of 2 trillion tokens, and a new BLT-1T dataset with 1 trillion tokens, both sourced from publicly available materials. Evaluation metrics include performance on various classification and generation benchmarks, such as common-sense reasoning tasks, e.g., ArcEasy MMLU, and coding-related tasks, e.g., HumanEval, where BLT's performance is reported in terms of accuracy and pass at 1 scores. Additionally, the paper employs bits per byte, BPB, as a tokenizer-independent measure of uncertainty, allowing for a direct comparison of BLT's robustness and efficiency against models using subword tokenization. The results demonstrate that BLT outperforms Llama 3 on several tasks, particularly in low-resource machine translation and character-level understanding, highlighting its advantages in handling byte-level information and noise.
What limitations or drawbacks does the proposed BLT method face, particularly regarding its implementation and generalizability across different domains or languages?
The proposed Byte Latent Transformer, BLT method faces several limitations, particularly in its implementation and generalizability across different domains or languages. Firstly, the scaling laws used for training BLT were derived from tokenization-based models, which may lead to suboptimal data and parameter size ratios for BLT, indicating a potential inefficiency in its training process. Additionally, while BLT shows improved robustness to noise and better character-level understanding, it may struggle with languages or domains that do not conform to the assumptions made during its design, such as those requiring nuanced handling of whitespace or specific linguistic structures. Furthermore, the implementation of BLT may not yet match the efficiency of existing tokenizer-based models in terms of wall clock time, suggesting that further optimizations are needed for practical deployment. Lastly, the reliance on a separately trained entropy model for patching could limit the model's adaptability, as integrating this learning process in an end-to-end fashion remains an unexplored avenue that could enhance its performance across diverse applications.